weird. Anyways, all right, let's get going. The reason I say this lecture is it's so loud. Can I turn that down? Maybe I'll turn this off. It keeps doing that. All right. Well, technical issues. All right. Again, Wichita, yell or throw things at the camera if you can't hear me on that stuff. So anyways, let's get going. Dosing. We calculated dosing. It's not difficult. Our doses were on weight last time. We talked about some body surface area stuff. This is just a little variation with the fact that not all drugs are dosed off of the weight of the drug. Okay, in this case, we're talking about drugs that are dosed in terms of their units of activity or their units of potency. So just read the quick definition on top. It says, when we do this, the activity of a drug or a biologic agent is determined by comparison to a corresponding standard. Okay, so it's not really the weight or the amount of the drug that's important. It's really the amount of drug that produces so much of an effect compared to a standard amount. So the point being is, when you talk about something that has units, is 100 units of that drug more of an effect than 50 units of that drug? Yes. The more units, the more activity of that drug. But you cannot compare the units of one drug to the units of another. So some common drugs would be insulin. Have you guys heard about insulin, right? Diabetics dose themselves by their units, the amount of units they need. They don't do it by weight, all right? Heparin is another big one we'll talk about in the next lecture. It's dosed in units of activity. But and again, so 10,000 units of heparin is more than 100 units of heparin. It would certainly produce a much greater effect, but we never compare the units of heparin to the units of insulin. They have no corresponding, so you only use it in reference to itself. So that's important. The other thing is, I agree that not many drugs are dosed in units, so when it is a drug, there have been a lot of medication errors. And again, insulin's a great example. Heparin as well is another huge example where, again, when a doctor's written for 100 units and written it as 100U, capital U, guess what it's been misinterpreted as? 1,000, okay? And unfortunately, they do make heparin in the concentration of 1,000 units per mil. And so it's led to 10-fold overdoses. So just be aware of, there's not many drugs, but when they are, take a special time to make sure that you got the dose right because there have been errors in the past. All right, let's do some easy breezy calculations to begin with. Getting you used to the term of units as a unit, all right? So a patient is taking 5,000 IU, and you'll see that abbreviation a lot. IU stands for international units. It's a standardization of a way to express the activity in terms of units. So 5,000 IUs of vitamin D3 daily for the treatment of vitamin D deficiency. If 40 IUs of vitamin D is equivalent to 1 microgram, how many micrograms of vitamin D is this patient ingesting daily? Right? That's a pretty easy one, but there's a couple of different things. I still say with these word problems, how do we set up a roadmap? So again, we're starting with, we're starting with IUs, all right? That's how much we know the patient has. So where are we going to go to? Well, we're going to go and start from there, and we're going to take this as it relates to this. In the end, that's where we're going to want to end up with is in micrograms, all right? So let's start with what the patient is taking, which is 5,000 IUs, all right? Then we're going to multiply that by this conversion, and this is where people will mess up. Is it 40 over 1 or 1 over 40? Use your unit. So we're going to multiply that by the fact that in every 1 microgram, there is 40 IUs, and we set the IUs on the bottom so the IUs units cancel, and we end up in micrograms. So 5,000 times 1 divided by 40 gives you the number of 125, and would you agree that the only units remaining, when you cancel these units here, the only units remaining are microgram? All right? Easy? Hopefully that's very easy. All right, let's go on. Let's do a permutation of that question, but apply it to a little bit of a different scenario. So here it says, a patient is taking 2 50 microgram capsules of vitamin D daily for the prevention of osteoporosis. And osteoporosis is, again, when you don't have you have brittle bones or the bones aren't as dense, and therefore if an older person falls, they can break those bones, their hip and their spine, so we don't want that to happen. So let's keep their bones as strong as possible. Let's give them lots of calcium and vitamin D. Vitamin D is very important for that. This patient, for some reason, doesn't want to take those 2 capsules. They want to go ahead and switch to a more natural source by taking cod liver oil. So here we have a product of cod liver oil that has 650 IUs of vitamin D per serving. And the question wants to know how many tablespoons full of cod liver oil would they need to take. All right? First of all, I don't care how lemonade-y it tastes. I don't think I want cod liver oil. That sounds disgusting. But anyways, I'm not here to question the questions. So this patient wants this liquid. Let's do it. But here's what I would kind of put you to. What is a serving? What is the USP? What is the standard definition of a serving? For example, we're going to have to talk about a teaspoonful here in a minute. What is the metric volume of a teaspoonful, if I say that to you? 5 milliliters, right? So it's got a definition. What is the definition of a serving? There is no set definition. Every product is going to quantify its serving different. I mean, you could look at potato chips. It could be per chip. It could be per bag. It could be per anything when you look at calories and so forth. So servings will vary depending on that specific product. So for us to be able to do this calculation, you've got to look to see how they define the serving. So come up here to the supplemental facts and look that they define the serving as what volume? 1 teaspoonful and give it a value of 5 milliliters, right? So again, 5 milliliters will contain 650 IUs of this, of vitamin D. Well, now that we know that, we have enough to get started. So where would we get started? Get started by what the patient is taking, what we know. They are currently taking how many capsules? 2. So 2 capsules times. How much vitamin D is in each one of those capsules? Well, they're 50 microgram capsules. So times 50 micrograms per capsule. Would you agree that units of capsules are canceling? So that's canceled. Now we'll take the 50 micrograms times the conversion that we were given in the previous question. We know that there are 40 IUs for every microgram. Okay. Now we want to set that up, though, so that micrograms cancel. So I'm going to put micrograms on the bottom so it cancels. So times 40 IUs for every microgram. Now I'm in IUs. Now I need to convert from my units dose to the volume of this cod liver oil. So let's multiply it by the fact that we just said the concentration has, for every 5 milliliters on top, there are 650 IUs. And why did we set up the concentration that way? So that these units cancel. I'm now in units of milliliters. I take milliliters, and that would be my answer, except for the question wants it in tablespoons full. So let's just finish that conversion and multiply it by another volume amount that you're going to have to kind of learn, is that a tablespoonful is how many mils? 15 mils. So we'll multiply it by 1 tablespoon on top over 15 mils. My mils cancel, and then I get my answer in tablespoons. And if you do the math from left to right all the way across, you should get the number 2. So 2 tablespoons is equivalent to 2 capsules for this patient. Any questions on that, other than why would anyone do that? All right, so next question. Let's make this ointment. This is exactly the ointment that it's discussed in this question, because this ointment is a 20-gram tube of ointment that contains 10,000 IUs, international units of penicillin G potassium, in the 20 grams. And if you take 10,000 divided by the 20, that's 500 units per gram. So that's what the question. So the question says, the contents of a vial of penicillin G potassium weighs 600 milligrams. That 600 milligrams of weight represents 1 million units of activity. That's the difference. That's why some drugs are expressed in their units of activity. All right? How many milligrams are actually needed to prepare this ointment that has 20 grams and a concentration of 500 units per gram? Okay? Any questions? That's what we're trying to set up. So there are some multiple choice questions here. I'm not going to do the question thing, the turning point, so let's just see. But I would tell you, if you look at the options here, do you see where you could go really wrong? You could go from a value of as low as 0.3 milligrams up to 16 million. And therefore, you need to have a little alarm bell that goes off in your mind about what's an acceptable range of answers, and check your own answer here. Things could go really wrong. All right? But this is easy. What are we going to start with? What are we trying to make? In the end, would you agree, the amount of penicillin we need depends on the amount of ointment. How much ointment are we going to make? 20 grams. So let's start with the 20 grams. I want to make 20 grams. How much penicillin G has to be in that 20 grams? Well, let's multiply it by its concentration as 500 units of penicillin for every gram. Would you agree the units of grams cancel? So now that cancels there. I'm in units. To convert to the weight of the penicillin G I need to provide that, let's just multiply it by its concentration in terms of units per gram. But in this sense, we need to make sure we have the right units in the right place. Since we have units already, we're going to want to put units on the bottom so that it cancels. So we would multiply it by the fact that we were told that 600 milligrams of this drug has 1 million units of activity. Units of activity is the denominator. It will cancel with the units from above, and our final units would be in milligram. So if you do the math, 20 times 500 times 600 divided by 1 million, you should get the number 6, and the final units are milligrams. So the weight of penicillin G we need is 6 milligrams. That 6 milligrams will provide us the 10,000 IUs of international units we need to put into our 20 grams of ointment, and that would give us the right concentration. Okay? Okay so far? Not too bad? Use your units, Obi-Wan. All right, so those goes to show all the different ways you could go wrong by doing that. I won't spend my time on that. All right, let's talk about morphine, man. I love morphine. Morphine is used in all sorts of treatment situations, and so it's available orally, it's available IV, it's available as suppositories in all sorts of different ways. So you'll see lots of different calculations with morphine. I want to clarify, before I get into the question, it talks about this patient receiving an intrathecal infusion, which is a little bit different, and it's kind of important for this question. So what is if I told you an intravenous infusion, would you know where that's going? Into your vein, right? So where's your thecal? Do you know where your thecal is? Intrathecal is your spinal column. It's basically a spinal tap. It's going directly into the central spinal fluid, going past the blood-brain barrier and everything else your body has normally to keep things out, okay? Which is good because it means we can give the drug exactly where it needs to go, but it creates risks in the term of, you'll see in our other questions when we talk about endotoxins and preservatives and things like that, that we absolutely need to make sure are limited or are not present when we put it directly into there. So that's why that's kind of an important part to this in terms of understanding the context. The calculations are the same though, so let's read it. It says, a 158-pound patient is to receive an intrathecal infusion of morphine sulfate at a rate of 0.3 milligrams per hour. So would you agree we have a rate of infusion in the rate of morphine per time? All right, that's important, so we've got that information. The solution is to be prepared by diluting, and again, this picture of this ampule is exactly what's used in this question, Infumorph 200. And 0.9% sodium chloride solution to produce an infusion rate of 2 milliliters per hour. So now it's not so much per weight of morphine, it's per volume of fluid per time. So we were given two different infusions here, different kind of quantities. Now this Infumorph 200 that we're using is both preservative-free and at a concentration of 10 milligrams per mil and comes in a 20 mil ampule. First question, how many mils of both the Infumorph 200 and of the sodium chloride injection are you going to have to use to prepare, and this is important, a 24-hour infusion, okay? Because would you agree, some of the things we know is the amount of morphine per what, though? Hour. We know the amount of fluid per what? Hour. A lot of those relationships, infusion rates, are a certain amount of something per time, all right? We also have a concentration in milligrams per mil. The only thing that's defined in terms of telling us exactly how much of this fluid we need is the length of time we're going to administer it. So we're making a bag for this patient that will provide the amount of morphine they need for how much time? 24 hours. So the start to this question, again, these are these word problems that are a little bit hard to start. Let's start with determining the amount of morphine we need to last how long? 24 hours. That's the key in terms of where to start with that. So let's look at morphine. And if we're going to calculate the amount of morphine that has to go into our bag, it's the amount that lasts how long? 24 hours. So let's start with our 24 hours and multiply it by, we know how much morphine we need per hour. We need 0.3 milligrams per hour. So if we multiply it in that expression, hours will cancel, and we will get the weight, the milligrams of morphine. But what we're trying to calculate is the volume of this additive, this ampule fluid that we're going to use. So we're going to have to multiply it by its concentration. But by the expressed as for every 1 milliliter on top, it contains 10 milligrams. That was given to us, but we're doing it in this way. So again, before I do any math, I always line up all of my units and make sure I understand the final remaining unit here. Okay, so if you do that math from left to right, the units will cancel and you should get a value of 0.72 numerically. And would you agree the final units are in milliliters? That's the volume of this additive. I need 0.72 mils of this fluid, this morphine injectable, to give me the amount of morphine I need to provide that rate for 24 hours. So far so good? Is the math easy, right? This is not about math, it's about setting it up and going in the right order so that your units cancel. Right? The only thing I would say, the next step, you might jump right into the sodium chloride, but there's an intermediate step. We have to do something before we worry about the sodium chloride. And the question we have to ask first, step back and just say, well, dude, how much fluid do I need? If I'm going to give this injection or this bag has to last for 24 hours, what's the total amount of fluid I need? That's an easy question to answer, really. How long does this bag have to last? 24 hours? Weren't we told how much fluid we're going to use per hour? We're going to use how much fluid per hour? 2 milliliters per hour. So if I take 24 hours times 2 milliliters per hour, my units of hours cancel, and I can see that 24 times 2 equals 48. What does 48 represent? The total amount of fluid that's going to go into this patient in a 24-hour period. So far, so good? So we know how much morphine? 0.72 ml. So the last question is, how much sodium chloride? And it's simply the difference between the total that has to go into this patient minus the volume for the morphine. And we said, so we take our 48 total, subtract the 0.72 that we need for the morphine, and the difference just is the amount of sodium chloride we have to use, which is the 47.28 mils. Okay? Would you agree if I take 0.72 mils of morphine and mix it with 47.28 mils of sodium chloride, what would my total volume be? 48 mils. If I infuse that at 2 mils per hour, how long will that last? 24 hours. Okay? Any questions on that? All right? Now, we're going to stay in the same scenario, but let's answer some different questions. And it gets back to why I said kind of knowing about the intrathecal thing is important. Because again, for intrathecal fluids, we have to be really careful with the amount of contamination that could be in there since we're going right past the blood-brain barrier. So the United States Pharmacopoeia, the USP, specifies a limit of 14.29 USP endotoxin units per milligram of morphine sulfate in solutions used for intrathecal use. So here again, we have a relationship that's talking about units, not weight. So again, we want 14.29 USP units per milligram of morphine, and a limit of 0.5 endotoxin units per milliliter of sodium chloride. What is the endotoxin load for this preparation? So how many endotoxins, what's the maximum endotoxins the patient might get using our IV product? Okay? Which one do you want to do first? Thank you for saying morphine. All right, so let's do morphine first. All right, so let's calculate the load of endotoxins being provided by our amount of morphine. Well, we got to start with the amount of morphine we're administering. What did we calculate before? What was our volume? 0.72, right? We calculated that, so that's the volume we're using. But our endotoxin is per milligram, so we have to convert that back to a weight. So let's take our 0.72 milliliters, multiplied by the concentration, expressed as 10 milligrams per milliliter, so that the units of milliliter cancel. Okay, we're in milligrams now. Now we can use the conversion factor they gave us that said that there was a maximum of 14.29 units per milligram of morphine. So if I multiply it in this way, then my milligrams will cancel, and my final units will be in units of endotoxin. So you do that math all the way across, and you get 102.9 endotoxin units. From which drug? The morphine. So the next step would be to calculate the amount that's coming from the sodium chloride. It's a little bit easier since we know the volume of the sodium chloride was the 47.28. Let's multiply it by the value they gave us as expressed as 0.5 units per milliliter, so we don't have to convert anything, but let's set it up in a way that my milliliters cancel. So 47.28 times the 0.5 units gives me 23.6 units total from the what? Sodium chloride. So the total endotoxin load, though, will be the combination of both of those. So let's take the 102.9 units from the morphine, add it to the 23.6 from the sodium chloride, and this whole patient is going to be getting 126.5 endotoxin units. Again, endotoxin is a protein expressed on a gram-negative bacteria. Do you want very many of those in your product going directly into your spinal column? Probably not. So the next question is that a good number or a bad number? I have no clue. How are we going to do that? So the next question says, well, here's the maximum. Basically, we're saying the USP is standardized that the maximum amount of endotoxin solution for an intrathecal injection should be no more than 0.2 units, see the capital U, per kilogram per hour. Therefore, does the compounded morphine infusion that we just came up with exceed that allowable endotoxin limit? Because that would be bad. We do not want to exceed that for this 158-pound patient. All right? So what are we going to do? Well, let's calculate the load for this patient. The amount, the 0.2 units per kilogram per hour, means we have to factor in the weight. So let's start with this patient's weight, 158 pounds. We'll convert it to kilograms by multiplying that every 1 kilogram has 2.2 pounds. Pounds cancel. We're now in kilograms. Now, I would highly suggest that you get used to setting up your units. When you see something like units / kilograms / hour in this case, set that up where you put the top unit, in this case units on top of the numerator, but just combine the lower two units like this. And the reason that is it allows you easier to see what units remain when you cancel. So for example, what is kilogram going to cancel with? It's going to cancel with kilograms. But we'll still have what units in the denominator? Hour. Does that make sense? So if I take 158 and divide it by 2.2, I get my kilograms. I take my kilograms times 0.2, and I'll get 14.4, and you can see that the remaining units are units of activity, units of endotoxin per hour. Okay, don't lose that hour. Is that okay? I'm kind of giving you a suggestion on how to set that up. Well, that's the maximum we can have. What did we calculate? Didn't we calculate how many total units this patient was going to have? Was 126.5, right? But that was just in units. But that was the number of units they were going to get because that bag lasts, how long did we calculate that bag to last for? 24 hours. So they're going to get 126.5 units over the 24-hour infusion. So if we take the 126.5 divided by 24, we get 5.3 units per hour. So is that a good number or is that a bad number? It's a good number. It's less than the maximum that it could have been, which was 14.4. So this is a completely safe preparation based off of limiting it below the maximum number of endotoxin units that it could have. Any questions with that? Sadly, I've run out of morphine questions. But I can move on to insulin because I will try to tell you, of all of the drugs that are dosed in units, insulin and heparin are the most important. So we can't not do an insulin question, all right? So let's bring this one up. It says, approximately 46% of insulin added to a total parenteral nutrition or a TPN bag is lost due to absorption to a polyvinyl chloride bag. All right? What the heck is that? Well, let's talk about that first. See, look at this picture here. I like this picture over here. That is a PVC bag. And again, this is a big one, white because it's got fat emulsion because it's a TPN. But have any of you worked with an IV bag that's soft and squishy, kind of a plastic bag? That's a PVC bag. We love those bags. Those bags are a godsend in pharmacy. You want to know why? Because when you hang the bag and you drain the fluid out, guess what? The bag collapses. The volume changes, so you don't have to vent. If you have a glass bottle and fluid drains out, guess what you have to replace into the glass bottle? Air that replaces the fluid so that there's not a vacuum that forms. You don't have to vent PVC bags because guess what the whole bag does? Shrivels up so the volume changes. You don't have to vent them. The fluid can just come out of them. So they're very convenient for administering IV fluids. That's why most of your drugs, or most of your solutions are in PVC bags. We love them. But we do acknowledge that there are some drugs, not many, but there's a few, that actually chemically react and kind of stick to the bag. So we have to take that into account. And that's what's happening in this question. Some of our insulin we're going to add is going to stick to the bag. So just keep that in mind. So the question continues and says, if 0.45 milliliters of U100 regular insulin, and that is a common way of expressing the concentration of insulin is U100, you need to know that to interpret that as meaning 100 units per what? Per milliliter. So that's the concentration, 100 units per mil. That 0.45 mils is injected into a bag, a 1 liter bag of this TPN. And we know this 1 liter bag is going to run at an infusion rate of 90 milliliters per hour. And again, how long? For 24 hours. All right? So the question is, how many units of insulin will the patient receive per day? This is kind of a cool question because it has this whole thing about the infusion rates and concentrations and all of that, and adds to one last factor about this absorption on there. So let's take it one step at a time. And you can certainly answer this question in multiple ways. There's not just one way of doing it. But what I would start with is let's just focus on the insulin. And don't worry about the loss or anything else yet. If I put 0.45 milliliters of U100 insulin into this bag, how many units am I adding? Simple question. 0.45 milliliters times 100 units per mil. Mils will cancel, and I will have units. So I am adding 45 units to this bag. So far, so good? Easy enough? Now, this is a trick you really just need to learn. So if you don't listen to anything else I said today, this is very helpful. In many questions and problems you deal with in pharmacy school, they will tell you X amount of loss. That whatever drug or whatever you're doing, you've lost this amount. In this case, what percent did we lose? 46% loss. I would argue it doesn't matter how much you lose. Do you know what matters? How much is left. I don't care what's lost. What I care is what's left, okay? Clearly, you have to use one to find the other, but let's do that. The next step would be determine, okay, I don't care if 46% is lost, how much is left? Well, take 100%, subtract the 46% that's lost, and the 54% represents the what? The percent that remains. So if I want to know how much insulin is in the bag, I need to account for the fact that only 54% will be remaining in my bag. I'm not worried about what's lost. I need to know what's still in it. So that conversion to be able to go from 46% lost to 54% left is important, okay? Now let's set it up and solve for this. And again, you can do it a couple of different ways. But we know that this bag is going to last for 24 hours. So let's start with 24 hours. We know that it's going to run at an infusion rate of 90 milliliters per hour. So 24 hours that it's going to run at 90 mils per hour. I now know how many mils of fluid I'll be infusing. Do I know the concentration of my insulin? Yes, I put 45 units into a liter, okay? Remember we calculated the 45 units and that went into a 1,000 ml bag, so the concentration of insulin in the bag is 45 units per 1,000 mLs. Now my mLs cancel and I have it in units. And here's the deal. If there was not any loss of insulin, that would be my final answer in units, okay? But we said the patient is not going to get all of that insulin. They're only going to get what percent of that total dose? 54%. So essentially then I'm multiplying it by 54%. I basically called my units and said that there are 54 units that remain out of every 100 units that I add. So that's where the 54% comes in. These units then cancel, and my final answer will be essentially the units of insulin that remain that get into the patient for over this 24-hour period would be 52.5 units. Okay? So that's that. All right, pop quiz, not again, don't freak out on this. So let's just give you the answers real quick. I won't go through this for the sake of time. I'm running out of time. But the answer for the one about the 4 milligram drug, you can see how I converted milligrams to grams. Here's the deal, a 1 to 750 ratio. That's the big part to that lecture. What is the units of weight per volume? Grams per mil. And in ratio strength, you just use whatever numbers I gave. So that's why you'll notice here, I used milliliters for my volume and grams for my weight and set it up so that my units would cancel, and I got 45 drops. All right? One on the bottom below is essentially, you can read it through there, the answer would have been 30. Rounding to a whole number is 30. So 45 for the one, the carbamazepine should have been 30. Sorry for the bad language in my question. Yeah, I didn't read so well. But hopefully y'all still got it okay. Did those questions look at all familiar? Like, do you remember if you look back, there was a picture of a phenytoin bottle for a patient, and I changed it to carbamazepine in different numbers, right? I went back and I looked at some of the good questions, not the hard ones, but some reasonable questions out of the slide handouts and reproduced them here. So I wanted you to kind of see that's what I will continue to do for the pop quiz questions, all right? Again, let me know afterwards if you have any questions. All right, I'm going to run out of time here real quick in 10 minutes. I don't know if I get through all this, so let me say this. Any questions so far? For the midterm exam coming up, the information that we've talked about, especially relating to the dosing, is super important. I wanted to use the last 10 minutes to kind of go through moles and molarity because I've already started recording some of the sections after the midterm, and I'm warning you now, this class does get a lot more difficult between the midterm and quiz 2 when we go through isotonicity and buffer solutions and electrolyte solutions and all of those things. And when I say it's more difficult, the math isn't more difficult, but it requires more chemistry. You guys remember your chemistry? You should. You've been closer, but some of you are not quite the chemists that maybe you should be at this point. So some of the terms, when we do electrolytes and talking about moles and milliequivalents to millimoles and all of those things, you get lost a little bit. So I'm just giving you a little bit of refresher here, and if I get through it all, so be it. If not, then it's on the video recording. You have to be strong. So here's some key definitions. I don't want to keep wasting my time. Moles. If I told you what a mole is, could you tell me what a mole is? And it's not the little thing you hit in the car in the middle of the night. It's, what is a mole? And let me ask you this. If I said you have a dozen eggs, how many eggs do you have? 12, right? A dozen defines a certain amount of eggs. That's what a mole is. Now, there's no eggs in it, but a mole is simply a quantity of molecules. And the reason we don't want to talk about individual molecules is there's a bunch of them. Can anyone tell me what a mole of molecules, how many molecules you have? And guess what? It doesn't matter of what. It can be molecules of anything. If you have a mole, like having a dozen, it means you have a certain amount. A mole is how many molecules? 6.02 times 10 to the 23rd. That's that avocado number. So what we want to do, I know that's not right, but I like that. Anyway, so instead, but we thank Avogadro for not letting us having to use those big numbers on our calculator. So what we're going to do is just say we're going to deal with it in moles. And again, if you have 6 moles, could you actually figure out how many molecules you have? Yes, you could just multiply it by that number. But let's just deal with the number of molecules in moles so we don't have to do this, just like we deal with eggs in dozens instead of doing them individually. All right? Things you got to know if you don't know this. By definition, a mole, the reason we chose that number, why is that such a funny number? That's the number of molecules that weigh exactly their formula weight. So 1 mole of those molecules will weigh their formula weight in what units, though? This is kind of important. Grams. The formula weight in grams is equal to 1 mole. All right? You guys kind of remember that? I mean, there's little examples of all of that here. So the reason I bring this up is that in biology, and certainly in pharmacy and chemistry, in the body, when we look at the amounts of sodium and potassium and magnesium and things and concentrations in the body, they're not that high. They're very low. So oftentimes we don't want to deal with moles or grams. We deal with millimoles and milligrams. So just understand that if 1 mole is equal to its formula weight in gram, what's a thousandth of a mole? would be a millimole. What's a thousandth of a gram? A milligram. So that same relationship holds true. 1 millimole of a chemical is equal to its weight in milligrams. So don't get confused with that, because a lot of my conversions, a lot of the work you'll need to do is in milli everything. And again, formula weight in milligrams is equal to 1 millimole. Okay? And lastly, what's important is molar. And I know you're going to have to know this for the next section when we go through those things, is molar is defined as a concentration. A molar concentration. Can you tell me what the units for a molar concentration are? It would be moles per liter. Per liter. Molar concentration is whatever number is, but in moles per liter. All right? We will often deal with things in millimolar. Millimolar is a little m, capital M. Millimolar means what? Millimoles per what? Per liter still. The volume doesn't change. So whether it's millimolar or molar, it's either moles per liter or millimoles per liter. Okay? You're already bored to death. Let's see if you can use this. So let's test your knowledge. This is a simple one. It says, you need to make 1 liter of a 0.9% weight per volume sodium chloride solution. How much sodium chloride do you need? And what is the concentration in millimoles per liter, which is essentially millimolar? I like this because it kind of takes back to chapter 6 a little bit too. So where do we start? Start with the volume we're making. We want to make 1 liter. So let's take 1 liter and let's first convert it to milliliters. And you'll see why here in a minute. So 1 liter times 1,000 mils per liter. So my liters unit cancel. I'm in milliliters. The reason I did that is that I know that the weight per volume units are what? What did I say? Weight per volume is grams per milliliter. But since this is a percent weight per volume, what does the percent mean? Percent means per 100, so it's per 100 milliliters. So 0.9% weight per volume. This is important. You got to be able to whip this thing out. That means 0.9 grams per 100 milliliters. Now my milliliters cancel. My final units will be in grams, and if you do that math all the way across, you should get 9 grams. 9 grams of sodium chloride per liter is equal to what? 0.9%. All right? So the question now is to say, well, let's express that in units of millimolars, or millimoles per liter. What I answered here is this 9 grams here per 1 liter here. That's that down here. So let's just re-express it as 9 grams per liter. And all we have to do now is convert our units. We're already per liter, so we don't have to change the volume. All we have to do is change the weight of sodium chloride in grams and convert it to millimoles. This is the key skill you need to be comfortable with. All right? So to convert grams to moles, what do we relationship? That 1 mole is equal to the formula weight in grams. In this case, we're going to leave it in that since we're already in units of grams. The formula weight was given to you at 58.44. So do you see where that number comes from? That number comes from right there in the standard relationship. We said that there's 1 mole for the formula weight in grams. Now my units of grams cancel, and I'm almost there, but I'm in moles per liter. To get to millimoles, I multiply by the fact that there's 1,000 millimoles for every 1 mole. Now I'm in millimoles per liter. You do the math, you get 154 millimoles, and that was expressed per liter, and that's the same as this millimolar, and that's what I mean by using this capital M. Millimolar means millimoles still per liter. Easy, I hope, or familiar, basic skills, but these are the ones we have to have. This is the last question, I promise. Let's just kind of still practice our unit conversions here. In this case, we're trying to make a medication cassette that contains 8 grams of carbenicillin disodium diluted to a total volume, final volume of 250 mils, but what we're using to dilute that is the 0.45%, and it doesn't say it, but if I tell you, it's weight per volume of sodium chloride. Okay? What are the millimolar concentrations of the carbenicillin and the sodium chloride in the final cassette? All right? So let's just set this up. Carbenicillin. Do we know how much carbenicillin is in our bag, our 250 ml bag? How much are we putting in? 8 grams. That 8 grams is going to reside in what volume? Total volume? 250 mils. So are you okay with where this came from? This is kind of setting this up. The 8 grams is what we're adding, and it's going to be in a total volume of 250 mils. So that's where we set up our concentration from. Right? Now, don't divide it out yet, because what we want to do is convert the units. I don't care about 8 grams and 250 mils, grams per mil. I need it in millimolar per what? per liter. So I need to adjust both of those units. Before I do any math, let's just convert it over. So the first thing to do is convert the weight, and you can do this in any order, but if I start with the weight of carbenicillin, let's go from grams to moles. So let's multiply by the fact that there's 1 mole has the formula weight. We were given the formula weight as the 422.4. So 1 mole of carbenicillin per 422.4 grams. My units of grams cancel. I'm now in moles. I'm almost there. But then I multiply the moles times 1,000 millimoles per mole, and I'm in millimoles. All right? So is everyone okay where that came from? The last step is to convert it to per liter. It's per 250 milliliters. Let's just multiply it by 1,000 milliliters per liter, and now my final units will be in millimoles per liter, and if you do that math all the way across, you get 76 millimoles per liter, which is 76 millimolar. Okay? Last step, and this I will warn you is the one where students would mess up the most. It has to do with this. What is the concentration of the sodium chloride we're using? 0.45% weight per volume. Okay, before we do anything else, re-express that for me. What does 0.45% weight per volume mean? What I'm getting at is this thing right here. You got to whip this thing out in your mind. Don't show me anything. Just in your mentally, you come up with this. 0.45% weight per volume is 0.45. What are the units? Grams. And since it's a percent, it's per 100 milliliters. So is everyone okay where this came from? All right, that's a concentration. Does it matter that we have 250 mils of that solution? No, I mean, we have 250 mils of that solution, but what is the concentration of sodium chloride in that 250 mils? It's 0.45%. So the concentration is the concentration regardless of the total volume. So that's why I'm not starting with the 250 mils. That doesn't matter. In this case, I know the concentration of my sodium chloride is going to be 0.45 grams for every 100 mils. Now I can convert that units the same way. And do you see where I lined it up just directly below where I did for the carbenicillin? Because you will solve it the same way. So to do it quickly, I'm going to start with my grams, and I'm going to convert grams to moles by multiplying by 1 mole over the formula weight of sodium chloride, which was 58.5. So my grams cancel. Then I'm going to convert my moles to millimoles by multiplying by 1,000. And lastly, remember, I got to get rid of those milliliter units by converting it by multiplying by 1,000 mils per liter. That means my last units are millimoles per liter, and it gets 77 when you do the math over to that. Okay? So surprisingly, I got through everything I think I needed to, but that was a little bit quick.